So hi to everyone. Thanks to the organizers for inviting me. Actually, it's a great honor to be here with so many, so great logicians and so way more knowledgeable about linear model theory than I am. So this talk is going to describe joint work. And thanks to Takahiko for actually pronouncing my name. I know it's a very non-trivial task. So this will describe some results from the last year joint work of Sandra about a tiny bit of very classical problem, a tiny bit which I don't think actually contribute to solving the problem, but as I said, it's a tip of it. So as you know, the constructions of AD actually produce, the constructions of axiom of determinacy we have always produce a model of something stronger. In particular, they always produce a model of dependent choice on reals. So actually of something stronger, which this is tradition I won't break, I won't define. It's traditionally not defined. Okay, so given that the audience is slightly more diverse and broader than usually in this kind of meetings, I decided to put a bit more definitions that are usually in the talks. So just recall that dependent choice means if you have, in this case, dependent choice on reals means if you have a binary relation on reals which non-uniquely for every element chooses another element, then you can actually thread through this relation. If you prefer, you can say that if you have a tree of reals of height omega, then you can find a branch. So this gives rise to the following problem, which seems to be hopelessly open, whether AD actually implies DC on reals. And we'll try to answer, as I said, a tiny bit of the problem. So now, of course, this, as I said, this is joint work with Sandra. Still somewhat in progress. Unfortunately, I was hoping to replace the main conjecture with the main theorem, but I will give you the main conjecture and then a proof of case of this at one level. Okay, so now the context. In 2000, I guess 19 or 20, Kanovei, Gitman, and David Friedman published a paper in which they produce a model of ZF for which, okay, so in the context they were interested in was context of second-order arithmetic. So actually, they stated it in terms of model of arithmetic. So there is a model of second-order arithmetic Z2. If you don't know what it is, it's not relevant for the talk. If you know, that was how they phrased it, in which axiom of choice, arithmetical axiom of choice holds, full axiom of choice. If you don't, and in which DC fails at pi 1, 2, at the level pi 1, 2. It's not paradoxical. Normally, of course, in set theoretical, yeah, I just figured out that this could be super confusing for set theory. So actually, if you think what AC can mean in arithmetical context, that there is no hope it will mean anything close to full AC. So it means if for every number you can give me a real, you give me a real, if there is the relation of this kind, and actually you can find a selector, right? So for every, you can actually find a uniform family of these choices. So you can find a function. Pardon? Every natural number, yes. Yes, yes. So this is closer to countable choice, actually. It's not contradictory. As I said, if for every natural number you can find a real for which certain formula holds, this is actually a scheme. Then there is a x such that for every number phi holds. Okay. Pi 1, 2 is actually also schematic, but pi 1, 2 can be expressed naturally. So for every real, there is a real such that some relation holds. Then for every, then you have one sequence of these reals such that the relation holds across the sequence. So as you can see, if you define this like this, then it's clear that the axiom translates very well to arithmetical context. Which is not relevant. This was just context. So if you missed something from the previous slide, I intentionally go past it. Like we can go back to it if you have any questions. Now the idea is looking at on what the construction they did looked like. Okay, so in the first place, they produced something that a model that in which dependent choice fails. So the idea is they actually use some properties of the model they start with, and these properties are actually are more or less saying that the model they start with is L-like. So now a natural idea is, well, take an L-like model as determinacy, do the same thing, and hope to show that the level of determinacy, so pi1k determinacy for certain level, so determinacy for pi1k sets, can be violated, so that the C can be violated in a model in which you have a controlled portion of determinacy. So, yes, this would roughly mean, of course, to the, like, which is a ridiculously small bit of the original problem, and which doesn't, necessarily push us any closer towards something that people actually cared about. But this one means that no level of determinacy implies the whole dependent choice, right? Like obvious as a trivial corollary. Okay. So as you can see, this is some leftover from adapting this talk to a theoretic audience. We forget, of course, about Z2, right? It's still now it's still a purely set theoretic construction. What you get actually at the end of the day is a model of ZF. Okay. As I said, we hope it's doable because if you just look at the proof, the construction they are doing is done originally over L. You look at the properties of L they are using, and you see that those same properties hopefully, and now this hopefully means verifying everything in between hold over, let's say, Mn. And well, you would like to show, actually the model they're producing is some kind of symmetric model. I will try to define, or at least to sketch the construction of, between a model of, with n Woodins, it's small forcing extension. So you can hope that actually pi1n determinacy holds in the intermediate model, even though it's not a model of ZFC. Why I'm saying this is that because, we've been asking around and looking in the literature, but there seems to be no proof of the fact whether, or no written proof at least, no widely known proof that existence of large cardinals proves determinacy over just pure ZF. But actually in the specific context when you are in a model which is an extension between, it does. Okay. As I said, this is a, like the theorem of the field in the presence of EC, and we'll show that in the specific context it can be saved. Okay, so I'm very strongly in favor of not calling something a theorem unless you have a written proof. So it's a conjecture, but like kind of work in progress conjecture. So not super open conjecture. That's literally what I called it in the first version of slides, and literally before this talk, I obsessing over, in the last turn of obsessing over slides, I went through this and said that no, come on, the theorem starts a stark violation of academic standards. No. Yeah, it's, I don't know, maybe. And actually, okay, so actually what I would normally call conjecture is to push it down to pi1n plus 2 to actually optimize it one bit lower. We have a, by the way, how far this game can go, we have a Cabal seminar result whose attribution I was looking for. And, I'm sure someone in the audience probably either knows the reference or is the reference. That actually pi1n AD proves pi1n pi1n DC of reals. So you cannot go with this game very, very much lower. So there is certain level by level implication. Do we know the answer? Maybe? Maybe. Okay. Oh. Okay, so what I will do here is to sketch the proof for the case n equals 1. And then make some vague remarks of how this transfers to higher ends. Okay. What happens in general? We start with a model which has, it's not only definable diamond. Of course, what's crucial here is the definable diamond that's uniformly definable across a class of definable models. Right? That, you know, like think of what your level by of what you know, how you prove sigma n well ordering of the reals. So let's say sigma 1 3 in this case, well ordering of the reals. We have a class of models across which you have a definable double well ordering which agrees, and in particular you have some canonical definition of diamond, which is the same definition across the among the whole models. As I said, you have some arbitrary. You have some kind of condensation that's awkward to spell out abstractly. So countable models. You have some kind of definable class of countable models, which have the same global well ordering, the same diamond, and are uniformly definable in a forcing absolute manner. Using this and following techniques by Friedman, Gitman, Kanovei, who actually followed techniques by Uri Abraham, and who followed techniques by Jensen, we define forcing, which is small, and that's produced a symmetric extension of M, where you have a pi1 free definition of generic tuple of the generic tuple of reals in a precise sense I will define, and the tree of all generic reals for the forcing will yield the definable failure of pi1 free. And now, since the forcing was small, and this intermediate model of a small forcing extension will be able to show that enough determinacy still holds in between. In this case, this enough determinacy means pi1 determinacy. We're working in n equals 1 case. Okay. As I said, like it's the classical theorem, the theorem of the field. I would not even put on this slide, if not for the broader than usual audience, that n plus, if you have, and I get this wrong, right? So n and n plus 1, of course, should be switched. More determinants, like n Woodins plus a measurable means n plus 1 determinants. And actually, it goes through the important class of models of ZF. So as I said, if you take small extension, a symmetric model in between, then this, the generic, notice that this is again a theorem star. When you have Woodin cardinals, the measurable above them, then it also satisfies pi1 n plus 1 determinacy. Yeah, maybe for the optimal result, we would like this model. I stated it for models of ZF and ZFC. Actually, we'll like in the optimal case probably to state this model for some class of models of ZFC, ZF minus. So replacing the top measure with a class. So now, as I said, like let's return to this. Pardon? Pardon? What is the? Yes, of course, P, yes, of course, P is smaller than everything relevant. Like P here will be of the size omega 1. Thanks. Okay, so let's turn now to this, to the details of the pi1 determinacy proof in order to make the details more manageable. To So we'll go to the details of this theorem star in the case of just one cardinal. So as I said, we're trying to check whether it's written up somewhere or known by someone, whether it simply holds in the context of pure ZF. You know, it's subtle. In the proof, especially in the projective case, you take some limits of models of which you say those limits are well-founded, but then you switch between well-foundedness in the sense of threading and well-foundedness in the sense of existence of a chain. The chain, what are they? They are chains of functions, so chains of something you know will not be in general well-founded. So, you know, you have to replace everything locally. Someone suggested, actually two people, once it was by Andreas, once someone else, that you can try to show that in N you still have all relevant sharps, but then you have to reprove Niemann's result that actually the existence of sharps implies determinacy, which means you want to find those absolute representations for pi1 n sets, which, you know, again, you have to prove something. So it seems that no matter which way you take, you end up checking the details of some known proof, which of course is kind of tedious work. In pi1 determinacy, I think it's simple enough to actually state here. First of all, in the pi1 proof, you can start with the following combinatorial characterization of pi1 sets, which is actually a theorem which holds simply in pure ZF. Namely, you can represent pi1 sets by the procedure of incremental building of orderings, which either will or will not be well orderings. So you can decorate the tree on omega less than omega with some linear orderings of initial segments of the natural numbers. So you plug in natural numbers in some, maybe even. So on the branches, you will decide, for instance, whether 0 is smaller than 1, then whether how is 2 located, then how is 3 located, and so on and so forth. So you're building some kind of linear ordering of the omega, and you choose precisely those reals along which the ordering you've built is well ordered. Right? That's a classic descriptive theory, I guess, maybe Martin or someone. Okay. Now, a subtlety that you might be worried, determinacy for closed games is not a theorem of ZF. Actually, it probably doesn't follow from ZF. Again, you know, like it's one of those small details you want to check, but determinacy for closed sets of reals is theorem of ZF. Why? Because on reals, because reals is omega to omega, omega is well ordered. So if you just take the natural proof of determinacy of closed games, you go to the leftmost point at which you haven't lost, which is not losing. And then you check that, you know, all the relevant sets are defined without choosing anything in the proof. But, you know, like it's thousands of details slightly that you have to check. Okay, so you work in N, so in this intermediate model now. So now we specifically go to intermediate model. You start with a game with a payoff set, which is pi1 as given by this family of orderings. As in the classic proof. I mean, it's essentially you go for classic proof and check what, like, small tiny details have to be checked. So as in the classic proof, you introduce an auxiliary game in which you make it harder for the guy that wants to get in A, right? So now please don't just produce a well ordering along the way, but also give me the exact certificate for this well ordering saying that this is the ordinal those are the ordinals whose order actually match the ordering you're building. So actually, along building the ordering, you now also build an embedding of this ordering, essentially on omega 1, but for the sake of the proof, we embed it into kappa. So now, this is still a game on well-founded set. So this explicitly, you explicitly give ordinals here, so it's still determined. Of course, if you win in the harder game, so if you win in this honest toil game in which you not only build a well-ordered set, but you also certificated explicitly why it's well-ordered, then by getting lazy again and forgetting about the explicit embedding, you have a winning strategy in the original game. Now we check that the proof for the second player holds up in this intermediate model. Okay, so the point is, starting with this U, you can define ultrafilter on kappa n by some kind of Ramsey condition. So this definition, notice, is completely choice-free. I just define a family of sets. I'm a big set if I contain a big clique, a clique on a big set. Right? So this is purely choiceless definition. And now now separately we check that this is actually an ultrafilter. Well, you sieve out the names. So you take a big set. In the measure U as viewed in V of G, it's a small forcing. So actually there's like how many names, how many forcing conditions can be responsible for it. Very small, so very small family. So there is essentially one forcing condition that forces it. So you have a big set in the original model below that set. And actually this big set in the original model, if you click on it, it's below a given set in a bigger model. So this shows that actually this Ramsey-like defined ultrafilter on kappa n, the definition itself doesn't use choice. The verification that actually it is still an ultrafilter goes down to the original model, applies the verification that used to be ultrafilter there, and then you go back and notice that this actually is an ultrafilter, because you can actually find a clique from the original model. And the rest of the proof goes just as in the original Pi-1 determinacy. You just go through. If you're at the position, the position in the game, you have only omega many choices for player 2. So kind of with probability 1, you know what kind of or what ordinal you could choose, right? So the set of ordinals you would produce that answer is big. So with probability 1, we choose without loss of generality what ordinals you used. Again, notice that this definition doesn't use choice. I said choose, but you don't. And you take whatever your response will be with probability 1, which is again uniquely defined, and so on and so forth. You can imagine this kind of details. You check that tau is winning strategy. Again, like this is now pure formality because this is really like in the classic proof. Take the game as played according to your strategy you defined in the augmented model. At each step, you took a Ramsey-like set in the ultrafilter and decoration from this Ramsey-like set. Now, working in V of G, you take this sequence of sets. In V of G, you'd not necessarily have the whole sequence. You use the same trick as before. Actually, you can now fix a good name for their respective intersection. Like you sieve them out, you take the intersection in the original, from the original model, you take a big set below all of them whose all kappa n's are in the every element of sequence. So you actually get one set in the ground model push every initial, like, such that n tuples for any natural n from that set will receive the same response in the game. And you're done. So you actually played with any betas from that big set. Those betas actually are ordinals. So actually the ordering you've been producing gets embedding into kappa. So actually the ordering you've been producing is according to the strategy and produces something from A, which is exactly as in the classic. You know, like, and in the projective case, you do roughly the same, only dilemmas are more complicated. And there are more of them to be checked. Okay, so now you go to the, now let's try to see what the model would look like. So as I said, it will be certain symmetric extension of the model of U. What we'll actually need is that it has a measurable cardinal, definable global ordering. By the way, this is not an abstract. No, I'm not trying to put an abstract conditions of this model. So like, I'm not claiming that whatever satisfies this will make the proof go through, because maybe there is some small clause in the between that I forget to put in and has some kind of a bit more technical and awkward definition. But generally what we'll use is that it has measurable cardinal, global ordering, as I said, uniform in a way, definable diamond sequence, uniformly definable in a way, a class of models which can uniformly form a global ordering, and they are defined in the absolute enough way, which is kind of subtle, that they will be definable also in the intermediate model, which is not a model of ZFC. You know, for instance, of course, the elements of hierarchy L alpha are, you know, like designed specifically for this purpose. In this, with this diamond model, you can define them in a way that also clearly is absolute. Like this class of model is absolute between all models, including models of ZF. Okay, what the forcing will be? Oh, maybe one remark about the general case of pi1n determinacy and this intermediate model lemma, so that the determinacy still holds in n in this general case. So what is the main workhorse over this case is that if you have an intermediate model between M and M of G, where G is generic for a small poset piece, a small poset, yes, sorry, is smaller than a certain measure. In this case, this measure will be, you should think of it as a first measurable. No, actually, in this case, this measure can be our measures, our measurables on which Woodin measures will live typically in the proof, sorry. So let's try to go through it slowly. So you have a measurable in M. You have a small forcing. You have a sequence of ultrafilters such that each of them, it's a coherent tower of measures. So each of them will be pulled back by projection to the previous, to the higher level. This is a situation you see all the time. So think of it, you have some kind of homogeneous representation for a set. You have this kind of tower of measures. And now it's kind of subtle where this comes from. So now you have some formula which probably in ZF essentially holds for the classes, right? So it factors through the functions that are ultrafilter equivalent. So I'm not saying now about classes or models or anything like this, because we're working in ZF, and you know, like ultra power is not a most fortunate notion. But essentially, think of it as that this phi is some property of functions of the ultra power. For instance, that they form a decreasing chain. They represent a decreasing chain in ordinals. right? So being a decreasing chain in the ultra powers means being smaller on ultra many, being smaller and smaller on ultra many points. So now you take a formula like this. So for instance, this being a decreasing chain. I get it wrong. Or for all. Yes. For any coherent family filter. Yes, I mean, like actually in the proof it's used only for very simple formulae. Precisely think of those. Like think the canonical example is that something is decreasing, but then you have, for instance, in the production of the models from the Martin-Still theorem, you have certain extra conditions, and like think of it that there are some simple combinatorial conditions one don't hold. And probably those are conditions that only depend on the on what happens on the ultra many places, and you somehow don't want to bother between like how this interacts between models. So for simplicity, you say that probably for all ultra filters this holds, and you write that I left an unfortunate parameter here. Okay, you have a parameter from N, so from the intermediate model, a sequence of functions which are from N. And now you want to say such that the values of those functions are from M, from the ground model. Again, think of the functions in ordinals, but we're working in slightly more generality. So then you can find a sequence of functions, whole omega sequence, equivalent to the original sequence, and satisfying the same thing. Now, equivalent to the original sequence, again, would probably... Okay, so the situation, like canonical situation I have in mind, which would probably be easier to digest than the whole lemma, which probably shouldn't be put here, is you have an ill-founded sequence, you have some procedure that produces you initial segment of an ill-founded sequence. You have a tower of measures, you're given those measures. The sequence of measures is in the ZF model. It doesn't necessarily come from the ground model. What is K? Yes. I mean, for every K is quantified. So with the best traditions of logic, a free parameter means a universal quantified statements, right? I'm joking, yes. For all K, yes. Yes. So for every, yes, maybe let me draw this on Blackboard. I know that this took more time. So you have, essentially the situation is this. You have a tower of measures. The measures themselves come from the ground model. The tower doesn't. The tower, think of the situation that the tower is indexed by some, the tower is indexed by indices coming from some real. The real is new. You have a decreasing, and now you want to say, okay, if I work in the actual forcing extension, so if I have choice, I would say this tower is ill-founded. So in the model, in the intermediate model, I actually have finite witnesses for each n, saying that this portion of tower is decreasing. This portion of tower can be decreasing. And you can actually find this in some uniform fashion. Precisely. Yes, precisely. This looks like an instance of the C.
But you only allow this instance.
But that's why there are so many tiny things in between. Like so many tiny assumptions in between. It's not a DC on reals. I'm not saying, I'm saying that the tower already exists of measures, and I want to produce essentially a witness to this tower being ill-founded. And this again goes through some careful sieving out names from the original model and this kind of procedure. But the point, very important point is that the real itself, so how the tower is indexed is actually already in the original model. Is actually in the forcing extension. Yes, I mean, it should be skipped. Yeah. For choice in M, I just say, like, yeah. It's for choice in M, it's trivial.
Functions with values
Functions.
What I'm saying is this seems to be
No. But like the function,
Sequence of functions.
The, okay. Maybe, yeah, I think it's right, but maybe I'll try to. I don't think the answer is wrong, but in the choice context, this would be a trivial. This would be a trivial lemma.
No, I'm saying.
These are
range.
You have some ordinal functions on defined on kappa. And if the like if the tower is ill-founded, then you will have actually, if the tower of the ultra powers is ill-founded, then you actually will find a sequence of such functions such that on big sets they will get smaller. The point, of course, being that the sequence is non-threadable. So of course, this would almost constitute like what you say almost constitutes a proof, but what you want to add is, and this is threadable, and this is precisely what you're saying is a proof. The threadability implies non-existence of such a sequence. Right? Sorry, I mean, yeah, I probably misunderstood your question, but maybe we put this to the break. Yes. I'm starting with a model of choice. As I said, like this is a global notation. M is a model of choice. MG is its small extension, N is. Yes, it's a typo. Thank you. I was a bit worried, like a bit afraid to go back this one slide. I see you're unhappy. I don't want people to be unhappy, so I'll try to make you happy in the break. I'm very sorry. Yes. 5 minutes. Okay, that's perfect. So Vienna people are now in the lucky position because when I was speaking about this last time, I managed to starting defining what the forcing is, and I didn't manage to get into any other anything else. Now I probably will skip what forcing is, but let's try to kind of rush through it. The pace of the other parts of the talk was a bit slow. Okay. What will the conditions of the forcing be? There will be some labeled finite subtrees of omega 1 to less than omega. Okay, so there are omega 1 branching, omega like less than omega height. Label PS. What is labeled finite subtree? Of course, a function whose blah blah blah. Function whose domain is subtree. Label at the node S. It will be iteration of length S, some finite iteration of forcings, where this forcings is certain family of perfect trees. The family of perfect trees will be defined inductively using diamond. So it will be growing at each step of the construction. So it will be iteration of certain forcing, and what I will iterate, which will be increased in every inductive step of the construction of that forcing. The generic will add certain tree on omega 1 less than omega decorated with reals. So I will make the trees get converge into some reals, and the tree will be growing. And crucially, it will satisfy the following fact. So this is a theorem. I said essentially Gitman, Friedman, Kanovei. Actually, back there is called modified or Kanovei-Lubiecki theorem, which means that I probably should put here essentially Kanovei-Lubiecki. Take a generic folded forcing with this pretty name. So a sequence will be Pn generic, well, Pn is the n iteration of the forcing you define at the end of the day, if and only if it's explicitly on the tree. For them, it's over L. And for us, it's over L of U. Yes. Sorry. Right? So you produce a tree of reals such that you can very explicitly define what's at the end level of this tree. The point is that the forcing itself, since it will be an inductive construction using diamond, coming from certain simple to define model, the forcing itself will be very simple to define. And by some properties of the forcing, the generics themselves will be easy to define in the final model, which you'll simply see that generic at the end will be something that was generic at every step of the construction. Pn was nothing. I haven't defined this. As I said, Pn is the nth iteration of the this forcing with perfect trees of certain class of perfect trees, which we'll get after performing the construction. Okay, basics of symmetric forcing. Normal filter of subgroups means that it's filter and it's normal. 0 minutes. Wrap up. I think, yes, you know about symmetric extension. I wanted to say, okay, so you take this funny forcing, you act by symmetric extension with the trees, by a group of trees which are countable and don't have a branch. You show that in the symmetric extension you will have a tree which won't have a branch. By the classical, like by the classic simple arguments. This tree, on the other hand, will be symmetric, so it will survive into the model N. And the tree will be coming from this construction, which will be kind of simple. So how the construction look like? This is about simplicity. Sorry. Yeah, most of the things. I think like locally the global minimum is valid. That for every slide there is a person for whom that slide is trivial, and this was my assumption. How just very quickly how the forcing look like. Okay, like slides probably will be now at this point just a distraction. So you start with the most trivial forcing with of perfect trees, which means you are only allowed trees that are node, and then full tree. This is the like smallest interesting forcing with trees. So essentially, only the stem matters. And then you're looking at the point in which Diamond says you have a model that looks like a candidate for your elementary submodel. If you see a generic folded forcing in that model, you take the trees from the generic and you essentially add them. Repeat. At the end of the day, the result is that if you find an anti-chain in your final model, take the elementary submodel containing that anti-chain, reflect it down. You guessed it by Diamond. So you actually have added some elements sealing that anti-chain. So essentially every anti-chain comes from intermediate models, which means that the generic at the end of the day will be something that is generic over every step of the construction, which will give you a definition of generic reals in the final model. I think this is the moment which I say Dankeschön.